So at the end of the day, we solve for these integration constants, and we find that C1 is negative Ts minus T infinity all over natural log outer radius over the inner radius. And then we looked at this as a ratio of resistances, K over H RO. And C2, then in our context, is TH plus TH minus TC, where this is T infinity, natural log of Ri, all over that same denominator. All right, and then our profile finally becomes temperature is our initial temperature minus, I'll put this out front, natural log of R, our variable, over Ri times ratio TH minus TC natural log RO Ri plus K over H times the outer radius. All right, so there we have it. And I won't be surprised if you do have some questions on this one, given that it was a little shaky in the beginning. So what kind of questions do you guys have on cylindrical systems and the solution that we went through this time? Yeah, the spherical one I said we weren't going to do. Anything? Sorry, so I guess the take home then is that let's just do a quick review of everything we did, and we'll try to chop out some of the uncertain stuff. All right, so to get here, we started with a steam pipe carrying multi-phase mixture of water and steam, so we didn't have a temperature change. We had a constant steam temperature of Ts. We had a pipe that was cooled by convection at the outside. For boundary conditions, we used the Dirichlet boundary condition of at the inner pipe radius we have the steam temperature. The other boundary condition we used was we balanced then the diffusive flux with the convective rate equation. The control volume we set up to analyze this was an annular control volume of volume 2 pi r delta z. Oops. We then balanced the heat flowing in and out of the control volume. We realized we had no generation, no accumulation, and so our conservation law became Q in minus Q out equals 0. We divided by the delta R length scale and did the limit of this as it went to 0. We took the limit as delta R went to 0 to find that the differential change in the heat flow as we move in and out radially is equal to 0. We applied Fourier's law. We typically have been applying it in the flux sense, where if we write Q double prime AS equals negative KAS, we let that AS cancel. This time, because the surface area changed, we included it. We actually used the full form Fourier's law, capital Q dot equals negative KAS dt dr. Once we plug that in, this AS was a single surface area. We took the limit as delta R went to 0, so there is no other surface to speak of any longer, and that surface area was 2 pi R delta Z. We assume K is constant. At this point, we also assume 2 and pi. Well, we know 2 and pi are constant. Delta Z doesn't change as we move in and out radially, so we're able to remove all of those, and none of those were equal to 0, so we found that ddr of R dt dr equal to 0. We used the product rule. So here what we did was use the product rule. And that product rule basically says that if we have the derivative of two things being multiplied, we can take the first term and take the derivative of the second term, that's this, and add it to the derivative of the first term, dr dr, multiplied by the second term, dt dr. So that's what the product rule told us. We landed on the Cauchy-Euler equation. So this is a very well-known equation, this d squared t dr squared plus 1 over r dt dr. And of course you put any variable you want in there. And we solved this with a u substitution. Or actually, technically, I think in a true sense, this is a reduction of order, is what we would call this u substitution. So we reduced the order. We went from a second order derivative to a first order derivative. So this is a substitution, but it's a reduction of order. So we got this to be a first order differential. We then solved this first order by separating it. This wasn't too bad to go through and separate. So we had 1 over u du equal to negative 1 over r dr. And we integrated this function, found out that the solution to this was, for u at least, it was c1 over r. U we had to back substitute because that was dt dr when we reduced the order of this differential. And so then dt dr is actually equal to c1 over r, and we chose some appropriate boundary conditions. We integrated that function one last time, looked at our boundary conditions, glanced at the solution to those, but then essentially were able to find C1 and C2 and the temperature profile. So that's the short recap of what we did in a much cleaner way, right, than what we did at the very beginning.